Okay, question number 6 on the moving coil meter. Consider the following statement made about the potential difference across XY of the circuit PQ shown in figures. Both shall have EMF, E and negligible internal resistance. Here, in case of these two circuits, when we have capacitors connected, so we have both equal capacitors connected, then we know the potential is going to divide as E by 2 and E by 2. And this will get completely charged and there is no any current flow. If we measure the potential difference across this is going to be E by 2. And in the second case, we have two resistors. So we know that it is a potential divider. And now if we measure the EMF across this resistor, it is going to be E by 2 because both of them have equal resistance. So statement A is correct. Statement B, if a voltmeter with finite internal resistance, so very important term, finite, that means it is not ideal, it is a real case, is connected across XY, it will read a steady non-zero voltage only in Q. Okay, so this is P and this is Q. If we connect a voltmeter over here, what is the case? So this is not ideal, okay? This is real. In case of a real voltmeter, how about the current flow through this? We have a current flow. We have a current flow through the voltmeter. Now, here, in second case, I mean in case of P, the capacitor is charged. Okay, so when we connect a circuit parallel to it, now it has a circuit to discharge itself. If this starts to discharge, then the potential difference will reduce. So the voltmeter reading will change. If this reduces, again it will get charged. Again the voltmeter reading will change. Therefore, there will be a changing voltmeter reading. In case of Q, it is constant. So how about statement 2? That is also correct. So statement C, we know that if it is an ideal voltmeter, then the current flow through it is 0. Then there is no current flow. That means both of them have to give the same reading. So that is also correct. Therefore, the fifth answer. Sarah, clear with that? Sarah, are you clear? Shall we move to question number 15? Question number 15. Of the following set of internal resistance given, the set of internal resistance that suit best for ammeter and voltmeter in order to measure the current I and the voltage across 1 kilo ohm resistor is shown. In the 15th question, it is simple. In a ammeter, the resistance has to be low. For a voltmeter, the resistance has to be high. Okay, so look at the voltmeter. It has to be greater than 1 kilo ohm. Just go through the answers in which it is greater than 1 kilo ohm. So the probable answers are 1 or 4. 1 or 4. The probable answer is 1 or 4. Now, go back to the ammeter. In the ammeter, we need the least resistance. So, among those two answers, the first one has the least resistance. Therefore, the first is the answer. Okay, Sarah. Shahama, do you have the 16th and 18th question? I have only up to the 16th question. Sorry, I mean up to the 15th question. Can one of you send it in the group? 16 and 18. Can someone send? Question number 16 and 18. Okay, in question number 16, we have three identical voltage source in a circuit ABC having negligible internal resistance. In circuit B, so this is the question. Those who didn't have, three identical voltage sources in circuit ABC have negligible internal resistance. In circuit B, uh, we represent a voltmeter having internal resistance R. So it has internal resistance. If R3, if R3 is equal to this value, which of the following is true regarding I1, I2, and I3? Okay, so let's look at circuit. Here, all the resistance are R2. Is the color visible? all the resistance are R2. So the only resistance that is changing is this over here. Okay. Now, what can you tell about the internal resistance of a voltmeter? Is it high or low? It is high. So the resistance won't be, this will be the least resistance. Okay, R1 will be the least resistance. Now, let's look at the current. We know that the current is now going to depend on this resistor R1. Okay, this is going to depend on this. Here, let's look at the equivalent resistance. The equivalent resistance is the product over sum. So instead of this resistor, instead of these two, we can write product R1R over R1 plus R. So that is equal to R3, right? That is equal to R3. Then these two circuits are identical. Therefore, I2 and I3 has to be equal. So we can cancel off these two answers. And here I2, I3, okay. So all the others are possible. All the remaining three is possible. Now let's compare these two cases. In these two cases, we know that the resistance here is going to be low because it is having a parallel connection, parallel combination. So I2 current has to be large than I1. Then I1 is less. So that is satisfied by which one? I2, I1 has to be less. I1 has to be less. I think there's a printing mistake. Here, this one should be I1. Does anyone have the past paper to check? Check the 2019, sorry, 2018 past paper. Shaham, what is the given answer? Fourth one. Here, it is I2 is equal to I3. It is I2 equal I3, right? Then printing mistake. Maybe this is I1. Then it will be correct, right? How about others? Clear with this question. Okay. How about the 18th question? Can you send that one too? Sarah and Saja, are you clear with that question? Question number 16. Uh, 16. Okay, Shama, you send the 18th question. I'll explain the 16th. Okay, here, sorry, the 17th. 17, in the circuit shown, the box with broken lines contains a resistor network. The 2-volt battery has negligible internal resistance. So negligible internal resistance is negligible, therefore it's 2 volt. Okay. An ideal voltmeter is connected across AB. So we have a voltmeter here. Ideal voltmeter. Ideal voltmeter gives a reading of 1 volt. When the voltmeter is replaced by an ideal ammeter, it indicates 2 milliampere. So if we have a meter, it is 2 milliampere. The resistor network inside the box with broken line is okay. So here let's see how we can deal with this question. If this is 2 volt, and this reads 1 volt, then this should be 1-to-1 potential divider. 1:1 potential divider, right? Okay, let's quickly go through the answers which are possible. Between these two, the voltage difference is 2 volt. If we connect a voltmeter, let's look what will be the reading. If we connect a voltmeter here, the reading will be 1 volt because current won't be passing through this. Okay, current won't be passing through this. 1:1 ratio, therefore 1 volt. It is possible. Now let's look at the second one. The second, if I connect a voltmeter, what will be the reading? It will be 2 volt. Okay, because these two are in parallel, then it should have the same reading. Therefore, fourth one we can cancel. Let's try connecting here. Here, if I connect the voltmeter, this also would read 2 volt because no current through this. Current through potential difference will be 2 volt. Therefore, second is also not possible. Third one is possible. Okay. Fifth one is also not possible. So is it clear how I selected 1 or 2? The answer has to be 1 or 2. Okay. Now let's connect the ammeter. Let's connect the ammeter. If I connect the ammeter, what is the equivalent resistance here? These two together half 1.5. So the total current here is 2 is equal 1.5 I. So that is 3. No. Equal to 3 by V is equal to IR. V equal IR. V is 2 volt. I is not known. This is 3 by 2. So I is equal to 4 by 3. So here we have 4 by 3. This is 1:1 ratio. When it divides, we won't get 2.5. We won't get 2 milliampere. Let's check this question. Here, if I connect a ammeter in this circuit, then this is short circuit. So 2 is equal IR. This is 1 kilo ohm. 1 kilo ohm. Then I is 2 milliampere. Therefore, third one has to be the answer. First tell me, are you all clear how I eliminated 2, 3, 2, 4 and 5? Is that part clear first? And the second part, finding the millimeter reading. Okay with that. Shahama. Okay, let's look at question number 18. Question number 18. It is actually a general knowledge question, like it is just like a general knowledge question. Here, an analog multimeter connected to a circuit is shown in the figure. The reading of the multimeter is, what is the reading? Now, first let's look at this switch over here. So when you look at this, you can understand this switch is rotatable, right? You might have seen these multimeters. And here we have an arrow that is pointing to one side. So what is that pointing at? Here, look, within this region, you have DC volt, okay? It shows DC voltage. So the answer has to be some kind of voltage. That is the first thing. Here, DC volt, right? It's not clear in the picture. Shahama, is it voltage? And here they have marked a value. What is that value? Is it 8 volt? Shama, is that 8 volt? Okay, what does that 8 volt mean? 8 volt means the maximum deflection. The maximum deflection is 8 volt. Now, what is the deflection? Okay, that is the question. Shama, it is 8 volt. If it is 8 volt, now look, it is more than halfway, right? The deflection is more than halfway. So the possible answer is 7 volt. I still have doubt whether it is 8 volt. If it was 2 volt, then the possible answer is 1.4 volt. Is the idea clear? Three of you gave the idea. If you got the idea, even if the question changes, not a problem, right? Okay, if it is 2 volt, if this is 2 volt, the maximum deflection is 2 volt. Okay, so here in this, the possible answer is only 1.4. No calculation needed. Okay, clear. Saja and Tara, all clear. Okay. Okay, so the topic for today is we have a few experiments to discuss. Determination of E and R. E and R of a cell. E is the EMF and R is the internal resistance. So case 1, we can use using a ammeter, voltmeter. So we can use a ammeter and a voltmeter. So this is the configuration. We have a battery and the battery is of EMF E and internal resistance R. We connect we connect a resistor, capital R. Now, what I want to do is, we know the equation, right? We can remember that V is equal E minus IR. So this is the terminal voltage. Now you have to measure the terminal voltage. For that, you will have to connect a voltmeter across the battery. And next, you need the current through this internal resistance. So it is the same current that is going to pass through the external resistor. So you can measure this current. So let's say this is a variable resistor. Okay. So V is equal to E minus IR. Now in this setup, we can change this resistance. When we change the resistance, the current in the circuit is going to change. Okay. So current is my independent variable. So we have V is equal minus R I plus E. So that is in the form y is equal minus mx plus c. Is equal minus mx plus c. Okay. So what we can do is we can change the value of R and change the current. So that is going to change the current. When current changes, your potential difference is going to change. So we can note down I and V and plot a graph. We can plot a graph. So if we plot a graph, we can expect for a negative gradient graph with an intercept. So from this graph, if I measure the intercept, that is going to be the EMF of the battery. And if we measure the gradient, that is going to be equal to the internal resistance R. So intercept C is equal to E and gradient is equal to R. Okay. So by adjusting the variable resistor, the current in the circuit can be changed. So here for the variable resistor, a rheostat can be used. Rheostat can be used to as the variable resistor. Since readings of R is not taken. Is it clear, this statement? You know what is a rheostat, right? In a rheostat, we can get continuous resistance, but we cannot get the reading out of it. We don't know what is the reading from it. Okay. So you must also know how to connect a rheostat. So rheostat is like this. We have a wire that is woven tightly around this. Okay, a wire that is woven tightly around this tube. And then we have another connector on top. So this can move. This can move. Okay. In a rheostat, there are several connections we can make. So A, B, C, and D. A question, don't note this. Can I connect? Can I connect between A and B? Can I make a connection between A and B? That means, can I connect a wire to A and another wire to B and make it a variable resistor? What is your idea? This is possible. Connections can be made between A and D. Here look at A and D. The current will flow in like this and go through the coil and leave through D. So if you move this, you are increasing. If you move this to this side, sorry, you are decreasing, because look, the length of the coil will reduce, right? If you go this way, so you can make a variable resistor. Any other combination we can have? How about A and C? Just think and tell me A and C, and what will happen when I move this side? Will it increase or decrease? A and C, can we use that configuration as a variable resistor? How about A and C? A and C is also possible, because here the current will flow through this, go into this, and through the coil it is going to flow out of C. Okay, so if you move this to your right, now the current will flow like this, go through the coil, and has to leave. So the length has increased. That means its resistance will increase. Okay, Saja. Sarah, the rheostat part for the experiment. Okay, so this rheostat, we can use rheostat as a variable resistor. Okay, the rheostat works on a simple basis. It has a very simple technique here. What happens is, we know that the resistance depends on length. if the length increase, then the resistance will increase. Here we have a very tightly woven coil. So just think, if that coil is stretched, then the length is really high, right? Now, in a rheostat, we can make several connections. We can make the connections in several ways. So here we have 4 connections. Uh, if I connect a wire to A and a wire to D, then this is how the current is going to flow. It has to go through this conductor, and through this connector, I use another color, through this conductor, and through this connector it will come to this coil, and now it will go through the coil like this, okay, and then leave through D. If I move this to my right, now just look, this is a very thick conductor. It is having very less resistance. So it will move through this conductor up to here, and it has to go to the coil over here, and now it will go through the coil and leave. So look at the second case and the first case. In the second case, the amount it has traveled through the coil is less, therefore the resistance is less. But in case of first, its length is high, therefore the resistance is high. Okay, Sarah. So now look, think about A and C. If we make a connection between A and C, will that work as a variable resistor? A and C, will that work as a variable resistor?